So in this video, we're going to discuss how to actually calculate changes in entropy, how to actually calculate values of delta S. So why is this important? Well, let's consider the two reactions below. So first example, we have liquid H2O being converted into gaseous H2O. Since we're going from a liquid to a gas, the molecules are becoming more spread out, more disordered, more chaotic. We would expect the entropy of this reaction to increase, delta S to be greater than 0. Therefore, we would also expect this reaction to be spontaneous, since the entropy is increasing. For the second reaction down below, we have aqueous sodium ions, aqueous chlorine ions being converted into sodium chloride as a solid. Since we're going from dissolved compounds, solutions, to a solid, we're decreasing the amount of combinations, we're decreasing the disorder, we're making the molecules more ordered, more in control, more specific. So the entropy, delta S, of this system would be less than 0. So this reaction is going to be non-spontaneous in this direction. Now, how much though? How spontaneous is this? How big is delta S? Is it 1? Is it 100? Is it 1,000? We haven't discussed how to actually calculate numbers for delta S yet. Same thing down here. How close is this to being spontaneous? Is it -5, -0.2, -1,000? We need to actually calculate the change in entropy. We need to calculate the delta S of these reactions. So that's what we're going to do in this video today. So if you're given any chemical reaction, here I give you a reaction where we're just using letters to represent any compounds. How do we calculate the entropy of this reaction? Well, the standard entropy change, delta S naught of this reaction is going to be equal to the products minus the reactants. So remember, anytime if we want to calculate the change in something, like change in entropy, is going to be the entropy final minus entropy initial, which in this case is entropy of the products minus entropy of the reactants. Same thing holds true here. This is also the same equation that we use to calculate the change in enthalpy, delta H of a reaction, except now we're just using entropy values. So we're going to take the coefficient of this compound C times the entropy of compound C, add it to the entropy of D times the number of moles of D. That's our products right here. Okay, boom, 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 minus the enthalpy of our reactants. In this case, A times the entropy of A plus B times the entropy of B. So that is the general form, the general equation for calculating the entropy of any compound given a reaction. You will also see this written as delta S naught of a reaction is equal to, this is what it is on your equation sheet, sigma sideways Z, which means sum of the entropes of your products minus sigma entropy of your reactants. This and this are the same thing. Small little note, this little naught, this is pronounced not at the top, means standard state. So these reactions are all conducted, these measurements are all done at the standard state, which is a pressure of 1 atm and 25 degrees Celsius. Different than STP, but this is the same conditions for thermodynamic calculations, so it's the same as it was for enthalpy. So how do we use this information? Well, let's say you have a problem like this. Calculate the entropy change of the reaction below using the information in the table. So here we have a reaction where a mole of nitrogen is reacting with 3 moles of hydrogen to form 2 moles of ammonia, NH3. So let's first predict. What should the entropy change be? What should delta S be? So always predict first? Well, I'm going from 1 mole of a gas plus 3 moles of gas, so 4 moles of a gas, to just 2. So since I'm having fewer moles, I'm going to expect the entropy to decrease. So when I get my final answer, I want to make sure that my delta S is going to be less than 0. If it's not, I know I probably did something wrong. So delta S naught of the reaction is going to be equal to the enthalpy of my products, so 2, coefficient of 2 here, times the enthalpy of NH3. So if I look in the table, enthalpy of NH3, 192.5. That's my only product, so I can end my bracket. Subtract it from, now let's do my reactants, okay? 1 mole of N2, so 1 times the entropy of N2, which is 191.5, plus 3 moles of H2 times 130.6. That is all my reactants. I end my brackets there. So I want you to go ahead and complete the calculations, but to double check, what you should get for a final answer is negative 198.3 joules per Kelvin. I know those are my units because those are the units of my entropies given in the table. So, follow-up questions we can ask. Does this agree with what we would predict? Yes, we predicted the entropy should be less than 0 because I'm going to fewer moles. What else does this mean? Is this reaction spontaneous? No, it's not spontaneous. Why is it not spontaneous? Because the change in entropy is less than 0. Now, in our next lesson, we're going to discuss Gibbs free energy, because you can't actually alone use entropy to predict spontaneity. You can't use it alone. There are some reactions that have an entropy less than 0 that are spontaneous, and we'll discuss how to figure that out when we talk about Gibbs free energy. For now, the main thing I would stick to is, if you're given an equation in the tables, can you calculate the entropy change? I could also give you the entropy change and ask you to calculate one of these numbers, which requires a little more algebra. And then you always want to predict and see if your calculation matches your prediction. Few key points that you need to know about calculating entropy. Number 1, the units. Okay, the units for entropy are always going to be joules per Kelvin. Okay? Coefficients. What do I mean by this? I mean, when you have an equation like 2a going to 3b, if you're calculating the entropy of the reaction, don't forget to multiply the coefficients in there. Otherwise, that's the easiest way to make a silly mistake. Last but not least, what does standard state mean? 1 atm, 25 degrees Celsius. That's all of these numbers that you'll get in tables. These are always calculated at the standard state. If we change the pressure or the temperature, these numbers change. And so we'd have to do something different. That's why we want to know that we're at the standard state. One small wrinkle. You may remember from enthalpy land, okay, molecules that are in their standard state, which we talked about being the diatomics and solids, we said the enthalpy of those was always equal to 0. You remember that? That is not true for entropy. Not true for entropy. Okay? For entropies, you never have an entropy of 0. You only have an entropy of 0 if you are at 0 Kelvin. Otherwise, you always are going to get a number that is a non-zero number in a table, or if you do the calculation.